Finally, let's talk a little bit about polar moment of inertia. The polar moment of inertia is defined as, for the entire region A, we have the integral of rho squared times dA. Notice that for this integral, the distance from the center rho is already defined in the polar coordinates. That is, we have the rho axis and also we have the theta. Well, you can ignore this notation if you think it is too complicated, but the basic idea is that adopt the differential area element in the polar coordinate system. As what we have discussed in tutorial 0, to do this integral, we can do this. J equals to the integral of rho squared dA. But you know, for the polar coordinate system, differential area dA is just rho d theta. Then we can compute the polar moment of inertia of a circular cross-section. J equals to rho squared dA equals to rho squared rho d theta. So this one is just simply dA. And also we consider the lower and upper limits of rho and the theta. For rho, its range is from 0 to r, while for theta, it is from 0 degrees to 2 pi. Therefore, we have the lower and upper limits of rho is 0 and r respectively. That of theta is from 0 to 2 pi. Then we have 2 pi times the integral. We have the integral of rho cubed d rho from 0 to r. So the polar moment of inertia is given by pi d to the power 4 divided by 32, where d is the diameter of the circle. Or you can express it simply in the radius, which is pi r to the power 4 divided by 2. Similarly, for the hollow circular tube, the computation of polar moment of inertia is rather similar, with one thing you have to modify, that is the lower and upper limits of rho. In this case, rho is from r1 to r2, so the lower and the upper limits will become r1 and r2 respectively. Similarly, you get this integral, and you evaluate this integral from r1 to r2, which gives you this result. And you can convert this result in terms of diameter, such that you have pi divided by 32 d2 to the power 4 minus d1 to the power 4.